a distinction you might have heard about between what's called narrow and general AI. So narrow AI is AI that's specific to one domain or task. The general AI is an attempt to create an intelligent version um, of a machine that actually has a human-like kind of intelligence. So narrow AI encompasses things like building cars that can drive themselves, building programs that can automatically analyze satellite imagery for intelligence purposes and so on, building programs that can run industrial robots and so on and so forth. So there's a tremendous amount of activity and success in all these and many more areas. And there's one particular kind of narrow AI that's worth singling out, and that's what's called deep learning. So you might be aware that computers currently are world champions in chess and Go, among other things. And that's quite significant, and it's doubly significant because they weren't programmed specifically to play those games. They were programmed to learn, and they were able to learn how to play those games better than the best humans. So the method for that is something called deep learning. It uses a structure called a neural network. And I'm going to give you a very, very superficial idea of how this works, but basically a neural network takes a bunch of inputs that represent a pattern. So the pattern might be where the pieces are on a chessboard, and the inputs that come in are essentially binary facts about it. So one of these little inputs on the left might represent that a particular piece is on a particular square, for example. And then given a pattern of inputs, it produces an output, and the outputs are on the right. And you might imagine each thing on the right here is to move a particular piece in a particular way in a chess game. And so the idea is the thing keeps looking at patterns, producing responses, and that's how it plays chess. And if we get under the hood a little bit, I'm going to give you an incredibly simple description of what's actually going on inside this neural network. So basically, it consists of things called nodes, which are these little dots here, and each node is kind of a binary thing. It's either on or off. And the idea is that as inputs come in, the inputs turn on certain nodes on the left-hand side here. And because this is a really tiny little network, so it's a little abstract to think about chess. So imagine this network is meant to learn something very simple, like let's say it's given descriptions of the parts of an animal on the left-hand side, and on the right-hand side, it's trying to give an output that correctly specifies what the animal is. So you might imagine the things on the left-hand side are, has a long snout, has floppy ears, has a shaggy tail, has four legs, things like that. And the things on the right are it's a cat, it's a dog, it's a horse, it's a pig, something like that. Okay, so the way this would work to try to classify an input, so a certain set of things are on in the input. Let's imagine it has a long snout, floppy ears, and a shaggy tail. Okay, that's what those three red dots represent. Now, based on that, the nodes on the next layer to the right decide whether they should turn on or not, and they do that in a really simple way. And basically, I'll take the network away for a second so you can see how simple this is. So each connection from a node on the left layer to the node to the layer to the right of it has a weight on it, which is a number. And so you take the nodes that are on, you take the weights on the links from them to a node to the right, and you add those weights together, and you compare it to a threshold number that's associated with this node over here. And if the weights are greater than the threshold, this node to the right turns on. If they're less than the threshold, the node to the right does not turn on. So I'm oversimplifying a little bit, so if you actually know how these things work, it's not quite a threshold function, it's a sigmoid function, and there are a few other things I'm leaving out here, but that's essentially how it works. So that incredibly simple algorithm gets propagated across this whole thing. So these three inputs might turn on two different nodes on this next layer, and those in turn might turn on two nodes in the next layer, and so on and so forth, and eventually we get an output. So let's say, for the sake of argument, that the output we get, we're actually looking at a dog, and the output we get is a horse. So here's where all the power of this algorithm comes. is we're going to train it to get better and better at recognizing animals. So horse is wrong. Okay, so we don't actually want this to be the output that goes with this set of inputs. We actually want it to be dog. Let's imagine dog is this here. So what we do is we want to, some people refer to this as sort of punishing. It's sort of like a big exercise in finger pointing. So all the nodes that were involved in this wrong answer, need to be punished a little bit so that they won't do this again. And of course, we're not really going to punish them. What we're going to do is we're going to reduce the weights. So if we trace back down this network, we're going to reduce the size of the weights between the nodes that turned on, and we're going to raise their thresholds a little bit so that they're less likely to turn on with the same set of inputs the next time around. Okay, so we make a little adjustment. We say, okay, that was wrong, so let's all the nodes and links that were involved in turning on the horse node output, let's calm you down a little bit so that you won't be as likely to respond that way the next time we see a similar pattern. And that's really it. So that incredibly simple thing just gets repeated over and over again. So to train this thing how to recognize an animal, we do maybe tens of thousands or even hundreds of thousands of repetitions of that, of showing it pictures of animals and training it up on whether it's classifying them correctly or not. And to do chess, of course, where the inputs are, where the pieces are on the board and the outputs are which piece to move, we have many, many more nodes, and we literally do millions, tens of millions, runs of this. So it's a big time-consuming thing. But again, you get this fantastically effective algorithm. So that's deep learning.